Welcome to Visual Algebra Lecture 1.4, Infinite Symmetry Groups. Previously, we've seen examples of symmetry groups of objects that have finitely many symmetries, like polygons. In this lecture, we'll look at infinite symmetry groups. The objects that these arise from, like my shirt, can repeat in 1, 2, or 3 dimensions, and are called friezes, wallpapers, and crystals, respectively. Let's dive in. In architecture, a frieze is a long, narrow section of a building, often decorated with art. You've seen these before. They were common on ancient Greek, Roman, and Persian buildings and elsewhere. Here's an example of one in St. Petersburg, Russia. Sometimes, but not always, such a pattern repeats. In mathematics, a frieze is a two-dimensional pattern that repeats in one direction, with a minimal non-zero translational symmetry. So with this picture, that minimal length is this right here. A non-example of a frieze is just a line, because this does not have a minimal translational symmetry. We can translate this by any amount, no matter how small. The symmetry group of a frieze is called a frieze group. A goal of this lecture is to understand and classify the frieze groups. Then we'll take a look at the 2- and 3-dimensional versions of these. Those are wallpapers and crystals. Here's an example of a frieze. And I'm starting with this one because I claim that it contains all of the symmetries that a frieze can possibly have. First, it contains a vertical reflection. We'll call that V. That's a reflection across this horizontal axis. I also claim that symmetries come in infinite families, and there's 4 of them. If we define T to be the minimal translation to the right, so that's translation by this amount, I guess 2 units if we call this a unit, then any power of t, t to the I for any integer, is going to be a translation. There's the first infinite family. The next infinite family are the glide reflections. Let's call GI the symmetry which is t to the I and then v. Now these commute, so we can do v first or second, it doesn't matter. So you translate by some amount by I steps and then you vertically reflect. Notice that v is actually equal to g to the 0. So this is, you don't translate and then you vertically reflect. So that's part of this infinite family. Next, there is a family of horizontal reflections. So across each one of these axes, you can reflect, and we'll call that HI. Notice you can reflect across these even axes, which bisect diamonds, or the odd axes, which do not. And finally, we can rotate 180 degrees around any one of these points, PI. And there's 2 types of points. There's the ones that are between a pair of diamonds, and then there's the ones that are not. The symmetry group of this frieze consists of the following symmetries. The set of all horizontal reflections, 180 rotations, translations, and glide reflections. Notice how I'm putting the exponent up here because this literally is t applied to itself, or t applied to itself I times, whereas GI, I actually want to be t to the I v. Notice that if I do G1 twice, then that's going to be, so if I do a glide reflection twice, that's actually going to be a translation. So it's v times t times v times t, which is t and v commute. So v squared, t squared, and v squared is the identity. So that's just t squared. So I don't actually want to take powers of these because any of these reflections squared is the identity. Any rotation squared is the identity. And any glide reflection to an even power is a translation. So these are actually the 4 infinite families. As I said before, notice that v is just g naught. And if we let h, r, and g denote the most basic reflections, rotations, and glides, so h is the reflection across this central axis, r is a rotation about this central point, and G1 is just a glide one step to the right, then we can say that this Frieze group is generated by any of these three symmetries. So you have to have one that has, I'm going to say infinite order. That's a term we'll introduce shortly. One that will never be the identity, no matter how long you apply it to itself. So a translation, no matter how many times you apply to itself, you are never going to get the identity. And a glide reflection has that property as well. So you have to have one of those in there. So either T or G. And then if you have any two of the three basic symmetries, either a horizontal reflection, a 180 rotation, or the vertical reflection, then I claim that you will generate this Frieze group. And if that's not obvious or apparent to you right away, it's not a bad idea to pause this video and play around with this and try it for yourself. And if you don't quite know how to do that, stick around, I'll show you some tricks. Here's an example of what I mean by tricks. If we number the diamonds like this with integers, then we have a notion of orientation, at least left versus right. And we can keep track of how many times we've applied a 180-degree rotation, at least if it's even or odd. Additionally, if we shade or color the top row of diamonds differently than the bottom row, now we have an orientation of up versus down, and we can keep track of whether we've applied an even or odd number of vertical reflections. Let's see why this is helpful with an example. H naught is also called H, is the central horizontal reflection, that is across the central axis. And H1 is the reflection across this adjacent axis. Let's see how H and H1 differ, like what group element or symmetry they differ by. Here's how we can do that. If we apply H naught, then the 0 diamonds are fixed and the 1 and negative 1 swap places. So we have this labeling. In contrast, if we reflect across L1, now no diamonds are fixed, 0 and 1 swap places, and then this 1 will swap with 2, and so we'll get 2's down here, and we get this configuration here. Now let me ask you, how are these two configurations related? It seems like one should be a translation of the other because they're both reflected. But which way? Is this does the translation go that way or the other way? And just looking at it, we can see that here are the zeros and then they're over here. So this frieze is a translation of that frieze. So this is T, and we can now say that this, which is H1, is equal to first doing H naught and then doing T. Remember, I'm reading from left to right rather than right to left like function composition. So this is a relation that holds in this Frieze group. Let's see how two consecutive rotations are related by a similar argument. So R naught is the rotation about this central axis. If we do that, that's going to make these negative and make these positive. But unlike up here where the dark orange diamonds stayed on top, it's going to bring the dark diamonds down here and the light ones up here. So these become positive, these become negative, and the shading gets flipped. If we rotate about P1, same thing. These are going to be, the top ones will be light, the bottom ones will be dark. But now, let's think. These are going to be zeros, these are going to be ones, and this will get swapped with the 2. So we'll get 2's, 1's, and 0's, just like up here, but this one, but the lighter diamonds are on top. So how do these two configurations differ? Well, it's by a translation, but which direction? Once again, if we translate this one to the right, we get this one. So the T goes this way. And that means that R1 is, once again, reading from left to right, R naught first do R naught, then translate. And it's straightforward to extend this, not just to the difference between 1 or 0 and 1, but between any consecutive reflections or rotations. And as an exercise, I'll let you think about how to compare H naught and H2, or H naught and H3. And the hint here is, well, let me just tell you the answer. H and H2 are going to differ not by t, but by t squared, and so forth. The frieze that we started with admits every possible symmetry that a frieze can. And now we'll look at other friezes that don't admit all of these symmetries. One way we can do this is by eliminating the vertical symmetry from the previous frieze group. And we can do that by removing half of the diamonds like this. In the process, we lose half of the horizontal reflections and half of the rotations. Notice how reflections across the axis L1 and also L3, L5, etc., they're no longer symmetries of this frieze. And similarly, rotations about P0, P2, P4, P6 are also no longer symmetries. We still have glide reflections, though. We have a G1, the glide to the right, and then we have G3, which is here, and actually G squared is a translation. So let's summarize this. So we have I call these the even reflections and the odd rotations, and then we have all glide, well, I don't want to say all glide reflections. I want to say that we have all powers of a glide reflection, and if you prefer, we can write this as, this is V times T to the 2I plus 1, where I is an integer. So this is, so remember in the previous slide, we called this G sub I, where G sub 2I plus 1, where I is an integer. So we have let's call them the odd glide reflections, the odd horizontal, the even horizontal reflections, and the odd rotations. So in some sense, we are losing half of the symmetries. Although in the other sense, we still have infinitely many, and half of infinity is infinity. But you know what I mean when I say half the symmetries. Here's a commutative diagram that shows you how G and H are related. And I'm doing this here, but we could have done this in the previous slide as well. So once again, it shows you how useful it is to label these diamonds. And notice that I'm labeling them a little bit differently. Well, actually, no, this is the same as the previous slide. So zeros, ones, twos, etc. But there's different ways that we could do this. Here I'm not using two different shades of color because I don't really need to. So if we start here and we do a glide reflection, we get the zero goes from here up to there. Everything shifts. And then if we horizontally reflect, so that's about this central axis right here. Now the 0 and the -2 become here. The -1 stays the same. And now we can recover everything else. So this is H. Now if we're here and we horizontally reflect, we get down here. So this becomes -1, this becomes +1, so 0, 1, -1, -2, -3, etc. And then we can ask, how are these two friezes related? And the answer is by a glide reflection. And my only question is, in which direction? So I guess this time I'm showing you the answer, but let's see why it is. So if you take this frieze and you glide to the right, remember that means that the 0 goes down here, you get this frieze because the 0 is down here. So in other words, I start with this, I do a glide, I do a horizontal reflection, and I say, how are these two things related? And now I have a motif that this Cayley graph is built with. And here is the Cayley graph. So you start with the identity. So we can label this with the identity symmetry, and this is a glide. This is G. So G is G1. Glide to the right. This is G squared, which we also know is from our previous frieze that is equal to T squared, because T squared. Well, again, G squared equals TV times TV, which is T squared V squared, because T and V commute. Notice that if you translate to the right and then you flip vertically, that's the same thing as flipping vertically and translating. At least I should say on the previous frieze, because translation is not a symmetry of this. But anyways, if you can just see it. If you glide twice here to the right, it is a translation. So that is just equal to T squared. So similarly, this is T negative squared, or T to the negative 2. So here's a Cayley graph of this frieze group. And we've seen this before. This came up in our lecture on presentations. That was the previous one, when we started with a Cayley graph of the triangle symmetry group, and we removed one of the relations, namely that r cubed equals 3. So instead of this arrow being a 3 cycle, if we got rid of that, we get that this frieze group is generated by a glide, a G, and H. H squared equals 1, just like in the dihedral group. GHG equals H. So in the previous lecture we had red, blue, red equals blue. But now we no longer have that this purple arrow. In the previous lecture it was red, forms a 3 cycle. So we get an infinite group. Let's see some more examples of friezes. If we eliminate all of the upper diamonds, now we've gotten rid of the vertical flip from the original frieze group and all rotations. But we still have all of the reflections. So we have the reflection across the central axis, which was L0, and then also all of these other axes as well. So this frieze group has all translations and all horizontal reflections. And a presentation is that, or it's generated by T and H, where H squared is the identity, and we have the same little motif, THT equals H. And this is what we saw in the dihedral group, and it's also what we saw in the second frieze in the previous slide. So these groups are going to be isomorphic because they have Cayley diagrams that have the same structure. Here's another thing we could do with the original frieze that we had, call it frieze 1. We could eliminate the vertical flip, and instead of eliminating rotations, we could eliminate all horizontal reflections. And we can do that by, instead of using diamonds, use something like crescent moons. Now we don't have any horizontal reflections across any axis, but we have all of the rotations. We have a rotation about P0, this is P2, but also about P1, and every single one of these original points. This frieze group is generated, well, where we say what it's generated by, it contains all translations. It contains all of the rotations. And so containing these two infinite families, it's generated by T and R. And I should say that R is the rotation about P0, just like how H here is the rotation about L0. So this has presentation or generated by T and R, where R squared is 1. And you can check that TRT equals R. Now you can believe me on this, or you can look at this and try to convince yourself, or you can do what we did in the previous slide and take one of those little commutative diagrams and label these crescent moons and check that indeed this, if you translate and then rotate and then translate again, that the end result is just a rotation. So again, here's that Cayley graph. This frieze group is going to be isomorphic to this one and the one in the previous slide. something else we can do. We can eliminate all horizontal flips and all rotations. And we can do that by preserving the translations and the vertical flip. So now this frieze group it contains all translations and all glide reflections, because the glide reflection is just a translation with the vertical flip. So this is generated by T and V. V squared is 1, but notice that TV and VT now commute. So TV equals VT. And you can, this one you can see a little bit easier. If you translate this thing to the right by one notch and then vertically reflect, that's the same thing as first vertically reflecting and then translating. So this Cayley graph looks like this. It's fundamentally different than these two and the one in the previous slide. Well, because it is abelian. The order does not matter. Take any two symmetries in this group and you apply them in either order, you'll get the same thing. That's not the case for these groups here. And I like comparing and contrasting these. This frieze we have no flips and no rotations, no horizontal flips. This one we have all of the rotations but none of the horizontal reflections. This one we have all of the rotations, all of the horizontal reflections and none of the rotations. And the previous one we had half of the reflections and half of the rotations. It's kind of a neat symmetry or duality here. Let's now put these together and construct a Cayley graph of our original frieze group, which let's call this frieze 1, and the frieze group, I don't know how to pronounce this, FRZ1. So this, as we said, is generated by translation and a horizontal reflection across here. But then we also need a vertical reflection if we want to get these top diamonds to be on the bottom. For a presentation, we need to say what each of these things, well, we need to say that H squared and V squared are both the identity, which is true for horizontal reflections and vertical reflections. H and V both commute, just like the rectangle symmetry group, a horizontal reflection with a vertical reflection. The order does not matter. And similarly, like the previous frieze group, if we translate and then vertically reflect, and then translate and then reflect down here, that's the same thing as first reflecting down here and then translating. So these two commute. And then finally we have to say how are T and H related, and we've already done that. We know that THT equals H. So this is not a proof that there's not other weird relations in here, but hopefully it's self-explanatory, or it's intuitive anyways, that if you have these three generators and you say that the two reflections squared are the identity, and then for every other pair you say how they interact, these two commute, and these two do not, then that completely describes a frieze group and the Cayley graph. So here is a Cayley graph, and notice how we are constructing it. We are piecing together the so-called tiles on the previous slide. So up top here is a Cayley graph for, I think, frieze 5 generated by T and V. So if I call this the identity, then this is V and this is T and this is T squared. This is H. And this is, over here, this is TV. So that's you can write TV, or you can write G1 for a glide reflection. Remember that a vertical reflection is just G0. Translate 0 and reflect. And it's not too hard to see that this is going to be G2. You translate twice and then vertically reflect. Over here is going to be G3, G negative 1, G negative 2, and so forth. And so in other words, remember those 4 infinite families? The glides are up top. So these are all the glide reflections. These are all the translations. So this is t to the negative 1. This is t to the negative 2. Then what about these? Well, this is h, and I claim that all of these are actually going to be horizontal reflections. So these are horizontal. And then these down here are going to be the rotations. And you can see that because if you think about the rectangle symmetry group, if you do a vertical reflection and then a horizontal reflection, you've done a 180 rotation. So that is going to be R, or if you prefer R naught, H is H naught. And so now all you have to figure out is where is H1? Is that one H1? Or is that one H1? Now we did that a few slides ago. Do you remember? We said if we had a frieze here. I'm not going to draw it. Well, let's see. We did H naught, and we got another frieze. I don't think I really want to draw this too much, but we did. Sorry, let me make that a little bit better. I'll just do it down here. H naught. And then remember, if we did a translation, we got another frieze, and we said that that was equal to H1. So that means that if you do blue and then red, you get H1. So if you do blue and red, you get H1. And similarly, you'll get H2 here. This is H negative 1. And by a similar argument, if we did so below that, we said if you do R naught and then T, remember this? That's the same thing as R1. So if you do start with your frieze, I'm not drawing them here. Think of this as abstract. And you do a green arrow. I really shouldn't draw this green. It's not the green arrow. It is. I'm drawing it green because it's a rotation. So if you do R, green arrow, and then red, you get R1. So if you do a green arrow, which, well, what's a rotation? A rotation is this, that. So orange, blue, and then T, you get R1. So that's going to be your R1. It's going to be your R2, R negative 1, R negative 2, H negative 2. And now we can see how these are all put together. These are the 180 rotations. And hopefully this is pretty pleasing to you, because now we can actually see how all these symmetries of a frieze are put together, and you can kind of see how there's no other symmetry that there could be of a frieze. Like there's every symmetry has to be one of these, and then the other frieze groups we've seen have all been subgroups of these. So one of them was just this top thing here. Now let's think about what the other one was. Another one was generated by a glide. Remember that? It was generated by a glide and a horizontal reflection. So where does that sit here? Well, the glide reflection is this. So a glide reflection is just orange, red. So if we add these, every time we have an orange, red, we put a purple. So we can do down here, we have. So now notice that well, we also need from here orange, red. So we also have this thing going here. And now this Cayley graph, think about what this was. I don't know if I want to add any more colors to this, but let's try. It contains the identity. Let me color that yellow. And then this was one generator. This was another one. So let's just follow all of the purple and blue arrows from these nodes. We get this one, and this one, and this one, this one, and this one, this one, and this one. So notice how we are zigzagging here, and we are skipping half of the translations, half of the glide reflections, and then down here, we're skipping, remember, the even reflections, rotations, and the odd reflections. So that is why we really are only getting half of the original symmetries. Now, it's totally optional, and I don't know if it's going to make this diagram worse, but let's give it a shot. We can add in the green arrows for 180 rotations. So 180 rotation is VH. So that's just this. So here are those. And now you can see this is a cluttered Cayley graph, but if I asked you to find find the Cayley graph of the group generated by, see, one of the earlier Frieze groups, I forget which one it was, but it was generated by a translation and a 180 rotation. I think that was like Frieze 4, maybe Frieze 3, one of those two. Then you can do a similar thing. You can start here and say, okay, what happens when you follow the red arrows and the green arrows? Let's see. Do I dare try this one more time? Yeah, let's see what happens. Let me pick a different color, and so if we do that, let's follow the red arrows. Well, we will get all of these, and then the green arrows, we get all of these. And yeah, okay, so now we can kind of see this one being diagonally in here. And so it contains these red arrows and these red arrows, and has the same structure of this. Okay, so I think it's helpful to see this, how they get pieced together, and how these other Frieze groups really arise as subgroups of our first one. However, we're still missing a few Frieze groups. Can you think about what else there is? Here's one. Since Frieze groups are infinite, each one must contain a translation, and one way to do that is to just take the glide reflections. This is a Frieze that only admits powers of glide reflection. So G squared is T squared. G to the negative 2 is T to the negative 2. And here's one last Frieze where we just have these moon shapes at the bottom, and these admit only translations. And here is the Cayley graph of that Frieze group. We can write these with presentations as being generated by G and T, respectively, subject to no relations. These are free groups on one generator, to borrow a phrase from the previous lecture, though we won't see that till a lot later in this course. And of course, these are isomorphic because they have Cayley graphs that have the same structure. In summary, we have seen 7 different Frieze groups, and that's all there are. But some of them are isomorphic, so we like to say that there are only 4 distinct groups up to isomorphism. So to summarize, there's these two, which are abelian. There's also Frieze 5, which was generated by T and V. This is also abelian, but it's not cyclic. These are generated by a single action, so they are cyclic. This one is abelian, but it's not cyclic. So let me write that. These are abelian, or I should say cyclic, and therefore abelian. Abelian, but not cyclic. Then there was Frieze 2, which is generated by G and H, which was isomorphic to Frieze 3, which was generated by T and H, which was isomorphic to Frieze 4, which is generated by T, and R. And then there was Frieze 1, which is the only one of these that required 3 generators, T, V, and H. We could have done T, V, and R. I just like having V as a generator because it commutes with T and it makes the Cayley graph easier to visualize. One thing I'll leave as an exercise is to construct a Cayley graph for the first Frieze group, and instead of using V, use R. So I guess you can, if you take the example that we did in the previous slide and you just remove, and you only keep the red arrows, the green arrows, and the blue arrows, you will get that. But it's nice to untangle those because remember the green arrows are crossing to arrange it a little bit neater. So I'll let you explore that on your own. Moving on, a frieze is a pattern that repeats in one dimension. So a next natural step is to look at discrete patterns that repeat in higher dimensions. And by discrete, I just mean they have minimal translational symmetry, like a frieze. A two-dimensional repeating pattern is a wallpaper. And by two-dimensional, I mean it has two-dimensional symmetry, whereas a frieze was a two-dimensional pattern that had one-dimensional symmetry. A three-dimensional repeating pattern is called a crystal. The branch of mathematical chemistry that studies crystals is called crystallography, and there's a lot of really neat group theory and difficult group theory in that. In 2 dimensions, patterns can have 2-fold, 3-fold, 4-fold, or 6-fold rotational symmetry. Think hexagons, squares, triangles, or 2-gons, or they could have no rotational symmetry, 1-fold if you may. I'll show you pictures of these really soon. Patterns can also have reflective symmetry, or if they don't, they're said to be chiral. We saw that with the molecule of boric acid in the last lecture. Symmetry groups of wallpapers are called wallpaper groups. These were classified by Russian mathematician and crystallographer Evgraf Fedorov in the late 1800s. In particular, he proved that there are 17 different wallpaper groups, in contrast to the 7 frieze groups in one dimension. Though some of these are the same up to isomorphism, mathematicians really like to say that there are only 17 different types of wallpapers. Even though there's infinitely many designs you could make, just like how the friezes we use diamonds, you could have used circles or squares or hexagons. There's only 7 types of frieze groups of truly distinct symmetries, and with wallpapers there are only 17. Here are those 17 types of wallpaper patterns, and the notation given was adopted by the International Union of Crystallography in 1952. So the numbers correspond to the rotational symmetry, 3, 2, 4, and 6. The M corresponds to a reflection, like a central reflection. The G is a glide, and it's a little more intricate. It's the MM versus MG. I think if you look at these, you can figure out really what they mean. But let me show you another picture of this. This is a little bit prettier, but I think it's not quite as regular. And one thing that's fun to think about is next time you go into a hotel or you go shopping for clothes or you look at a pattern, whether it's on tiles or the wall, think about what's the symmetry group. You will find all of these somewhere, around on clothes and designs, but some of them are more common than others. And it's fun to think about like which one is which and which of these do you see around more often than others. Okay, let's now move from 2 to 3 dimensions. Symmetry groups of crystals are called space, crystallographic, or Fedorov groups. They were classified by Fedorov and Schoenflies, who is also a crystallographer. In 1877, they proved that there are 230 space groups, and they classified them. Now that I say 1877, that's the same year as the previous result for the wallpaper groups, and I'm wondering if that's right, or if I have one of these dates a little bit off. Anyways, it's the late 1800s, regardless. In 1978, a group of mathematicians showed that there were exactly 4,895 four-dimensional symmetry groups. This is, I think, more recreation than anything. I can't imagine this is really that useful. I don't know, maybe in physics it is. And then in 2002, it was discovered that two of these were actually the same group. So there's really only 4,894, which for me anyways, begs the question of how confident are they that they didn't double count one of the other four-dimensional symmetry groups, and maybe there's fewer than this. I don't know, it was peer-reviewed, but there have been other mistakes found in peer-reviewed papers, especially when they are large classification theorems. I wouldn't bet too much on it. Okay, so that is a good place to stop. In the next lecture, we will learn about something called a Cayley table, which is really the group theoretic analog of something that you've seen in grade school. Multiplication tables and addition tables for arithmetic. We can do the same thing for groups. We'll learn about that. We'll see a new group called the quaternion group that will be with us for the rest of the class. And then in the lecture after that, we will finally get to the formal definition of a group. And we'll see some pitfalls about why we can't quite use a Cayley graph definition or a Cayley table definition. So there's a lot of fun stuff coming up, and my favorite material from the next two lectures you will not find in any other algebra textbook. So stay with us.